dropping your whole everything. A band is blowing Dixie, double fall time. You feel alright when you hear the music ring. Now you step inside, but you don't see too many faces. Coming out of the rain, they hear the jazz go down. Competition in other places, but the horns, they blowing that sound. Way on down south, way on down south, London town.
Okay, hello everyone, and welcome to the very last edition of Physics 270, where we learn to appreciate and to love physics. This semester is coming to an end. Our finals are right around the corner, and we are still at home dealing with the coronavirus crisis. Now, if for whatever reason you are feeling a little bit pessimistic, then I have this quote to share with you that is by the one and only Winston Churchill, who was Prime Minister of the United Kingdom during World War II, and he said, "For myself, I am an optimist. It doesn't seem to be much use to be anything else." So I hope you are able to stay optimistic, keep looking at the bright side of life. Now, last time we discussed a little bit about how objects move when they are in fluids. We discussed what the pressure is in a fluid as a function of the depth in the fluid of the point you're considering. And today I'd like to continue talking about that. And ideally, we would also discuss how fluids themselves move, do some fluid dynamics. However, we will not, unfortunately, have time to do that. You are welcome to read the chapter in the book, chapter 14, the rest of it. So today we're going to talk a little bit more about fluids, and specifically I want to discuss the concept of buoyancy, which is a kind of a funny word. We'll get to that. But before we do so, let's make sure that we remember what we learned last time by looking at example 14.3. Example 14.3, which is on page 421. And you are asked to estimate the force exerted on your eardrum due to the water when you are swimming at the bottom of a pool that is 5 meters deep. So here's the pool, there's the pool, there's the water, and you're down there, you're at the very bottom of the pool, and the pool is 5 meters deep, and you are asked to find the additional force that your eardrum experiences compared to when it's out here, when you're at the bottom of the pool. So we're looking for that additional delta F that you're going to experience down there at the bottom of the pool. And you are given that your eardrum, or I guess maybe we'll have to just estimate, but your eardrum, we'll consider it to have an area. The area of your eardrum is going to be 10 to the negative 4. 10 to the negative 4 meters squared. So with that information, you'll remember that the density of water is 1,000 kilograms per cubic meter. So if you have a cube that has length, side length 1 meter, and you fill that with water, then the weight of the water in there is 1,000 kilograms times g. The mass of the water in there is 1,000 kilograms. So we discussed last time that the change in pressure, so if outside the pool right there you have atmospheric pressure P0, then the additional pressure that you experience inside of the pool, that delta P, this is what we're looking for, the delta P that you're going to experience is going to be equal to rho, the density of the water, times g, the acceleration due to gravity, we're going to assume you're on Earth when you're doing this experiment, times the depth, h or d, and in this case that depth or that h is equal to 5 meters. So we want to plug in 1,000 kilograms per cubic meter, 9.8 meters per second squared, and a depth of 5 meters. But that will give us the change in pressure. We were not asked for the change in pressure. We were asked for the change of the force experienced. And we just have to remember that the change in pressure is just the change in force per area. So pressure is force per area, and that is going to be equal to rho water GH. And therefore, from here, we can solve for the additional delta F. That delta F is going to be rho water GH, and then I just have to multiply both sides by the area. And so my final answer is that that force is going to be the density of water times the acceleration due to gravity times the depth times the area of your eardrum right there. And if you put that all together, the additional force that you experience is about 5 newtons. 5 more newtons acting on your eardrum when you are at the bottom of a pool that's 5 meters deep. Okay, so with that, you hopefully remember what the pressure looks like in a fluid as a function of the depth, and I am now going to use that to introduce the concept of buoyancy. Buoyancy. So buoyancy is kind of a funny word to pronounce. Try saying it out loud if no one can hear you. Buoyancy, 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 buoyancy. But it's also kind of funny to spell. It's a bit tricky to spell. I mean, if you were just reading it phonetically, you might not call it buoyancy. You might pronounce it buoyancy or something. But let's use the fact. I'd like to use the fact that we just recalled right now, just a moment ago, that the change in pressure as you go down at a certain depth in a fluid is density of that fluid times g times h, where h is the depth from the surface down to the point that you're looking at. And I want to consider some object that I have immersed in some fluid. So here's some bucket with some fluid in there, and then I place some object right there inside of the fluid. And of course, the pressure, the fluid is going to have some pressure as a function of depth that we've already discussed up here. But notice that the pressure at this point right there, just above the object, right there, is going to be, of course, smaller than the pressure of the fluid down here, right? This lower end here is at a deeper point than the top one, and therefore the pressure at the bottom end is going to be greater than the pressure at the top end. So in other words, there is a pressure differential acting on this object. The pressure below is greater than the pressure above, and therefore, since the pressure below is greater than the pressure above, then this object is going to experience a net force upwards. Remember that the pressure is just the force per area. The force per area at the bottom here is going to be, as we said, greater than the force per area at the top. And so the object is going to experience a net force upwards. And that's just true whenever you find yourself in a fluid. You experience that when you're in the atmospheric fluid, the atmosphere, you experience a net force upward. You can't really feel that, but you've definitely seen balloons full of helium float upwards, and the reason is that they are experiencing a buoyant force due to the change in pressure. The pressure the balloon experiences below is greater than the pressure that the balloon experiences from above, and so there is a net force upward. So this is a buoyant force, and I'd like to use this object over here to derive quantitatively what that buoyant force depends on. So we're going to assume that there's a face that looks downwards here that has an area A, and a face above that also has area A, and therefore this change in pressure is, again, just like in the last problem we solved, it's going to be delta F divided by A, that is equal to rho times G times H. Remember that this rho, I'll just write it rho W, is the density of the fluid surrounding your object. And so if we want to know what the net force acting on the object is, all we have to do is solve for delta F here. So delta F is going to be density of the water times G times H times A. Now by H, what I mean is the delta H. Okay? The change in pressure from here to here depends on the change in height from here to here. But if you multiply the delta H, that delta H, by the area, what you get is the volume of this object. So really, I want to multiply the density of the water or the fluid times G. If I combine this A with this delta H over here, what I get is the volume of the object. So let me just write that down. So there it is, rho, density of the fluid times G times volume of the object. Now you can read that right there. It says object, right? No, it does not say object. Why does it not say object? It says IMM, which stands for immersed. It's the volume of the object that has been immersed. Now in this case over here, the object is fully immersed, and therefore the volume of the object is equal to the volume of the object that has been immersed. But what if you had some object that was floating? Like that. Now, it is not the whole volume of the object that you want to plug in here, but only the volume of the object that has been immersed. Because at this point over here, what you have acting on you is no pressure due to the fluid. It's just the atmospheric pressure you had previously. So to find the buoyant force acting on an object, you want to multiply the density of the fluid that it finds itself in times gravity times the amount of volume of the object that has been immersed. This volume can be as little as almost zero if your object is barely immersed in the water, or it can be as much as the full volume of the object. It can't be more than the full volume of the object, and it can't be less than zero. Okay, so let's now discuss what happens when we compare this buoyant force to the other forces acting on the object. Now, let's look at this object right here. This object we just derived is experiencing an upward force due to the change in pressure in the fluid it's in. That upward force we call buoyancy. There, I could even spell it. But there are other forces acting on the object. For example, you know that the object experiences a downward gravitational force whose magnitude is mg. Now let me ask you, what would happen if mg were less than the buoyant force? If the buoyant force that we derived here has a magnitude that is greater than mg, then the object experiences a net force up, and therefore the object is going to accelerate upwards due to gravity. So that perhaps happens if you have like a basketball that you try to immerse in water. The gravitational force of the water, the gravitational force acting on the ball is probably less than the buoyant force that is pushing the ball upwards, and so the ball is going to float upwards. What would happen if the gravitational force were greater than the buoyant force? For example, if you have some kind of rock, if you take a stone and you throw it in the water, then yes, the stone is going to experience an upward buoyant force, but the buoyant force is not enough compared to the gravitational force. And so when that gravitational force is greater, the object will sink downwards towards the bottom. And what happens if the two are equal? If the buoyant force is equal in magnitude to the gravitational force, then of course the object will just stay there. Now that you've probably experienced when you've been given a balloon for your birthday that was full of helium, and then as soon as you let go, it kind of goes upwards. It accelerates upwards, but that only happens the first few days. After a few days, the balloon starts to lose helium, and at some point you notice that you can grab the balloon, bring it lower, let go, and the balloon is still right there. Okay, so it doesn't accelerate upwards and it doesn't accelerate downwards. At that point, the force of gravity pulling it down is approximately equal to the buoyant force holding it up. Okay, so this is a little bit about how the buoyant force works. Remember that it depends on the density of the fluid you find yourself in, the acceleration due to gravity, and the amount of volume of the object that has been immersed. And so next, I'd like to help you understand what percentage of an object is immersed when an object is floating on the surface of some fluid. Okay, so let me just write that down again. We just found that the buoyant force, the force of buoyancy, is equal to the density of the fluid you find yourself in times g times the volume of the object that has been immersed. And so if an object is totally immersed, then this V immersed is equal to the volume of the object. But if an object is floating at the surface of the liquid, so if you have, as I showed before, here's some fluid, here's some object right there, and that object is just floating right there. If the object is floating, it's not moving, then it must be the case that the net force acting on it is equal to 0, which means that the buoyant force is equal in magnitude to the gravitational force. Now you know that the gravitational force is equal to mg, and we know that also it is not the case that the full object is immersed, but you have some V immersed over here that we would like to explore a little bit further. So we know what the buoyant force is. The buoyant force is just the density of the fluid times g times V immersed. And we know what the gravitational force is. The gravitational force is m times g, where this is the mass of the object, m of the object. But I can now relate the mass of the object to the volume and the density of the object. Remember that the density of the object is equal to the mass of the object divided by the volume of the object. So I'd like to replace the mass of the object by the density times the volume of the object. So the g's here are going to cancel, g's cancel. On the left-hand side, we're left with rho of the fluid, volume immersed, and then on the right-hand side, I have the density of the object and the volume of the object. And so for my final trick, I'd like to show you that the ratio of V immersed, so if I now solve, let me rearrange what I've written here, V immersed divided by V of the object. The ratio of V immersed to V of the object is equal to the density of the object compared to the density of the fluid. So this shows you that the percentage of the volume of an object that is immersed depends on the relative density between the object and the fluid that it is immersed in. So if the density of the object is equal to the density of the fluid, if this is equal to 1, then the V immersed is going to equal to V object. In other words, if this were just the same as the fluid, then it would not be floating above the fluid, it would be fully immersed. Now the greater, the lower the density of your object is, the lower V immersed is going to be relative to the object. So the amount that is immersed gets smaller and smaller. In other words, more and more is floating above water as your density of your object becomes smaller. So this is the condition that allows us to understand what percentage of an object is going to float above water and what percentage is going to be immersed in water. All we have to look at is the relative density between the object and the fluid that it has been immersed in. So let's check to see that we understand this relationship. Let's look at example 14.6, which is on page 427. And what we're talking about here is an iceberg. So I'm going to keep that relationship right there. I don't want to erase that. So we're talking about an iceberg that is floating in seawater. So that looks something like this. Here it is. You have some kind of, here's the iceberg, and it's sort of floating in seawater. I hope you can see the level of the water, the iceberg. This iceberg, we are told, is extremely dangerous because most of the ice is below the surface. Right? So you've probably heard of the Titanic. People saw the iceberg. They weren't able to maneuver away from it fast enough to avoid the collision. But in any case, icebergs can be tricky. They can go out far from where you see the tip. So the hidden ice can damage a ship that is still a considerable distance from the visible ice. That's the visible ice. The question is, at what fraction of the iceberg lies below the water? So they're saying, what is V immersed compared to V object? What fraction of it is immersed? What fraction of the iceberg lies below the water level, given that the density of ice, which our object is made out of, the density of ice here, our object is made out of stuff that is 917 kilograms per cubic meter. And our object is, the ice is immersed in a fluid, the seawater. And so the density of our sea fluid is 1,030 kilograms per cubic meter. So we've been given these two numbers, and all we are asked to do is compute the ratio to find the ratio of the object that is immersed to the object that is, to the total volume of the object. So once you do that, you divide those two numbers, you find that this ratio over here is equal to 0.89. So this is equal to 0.89. In other words, about 89% of the ice, of the iceberg is immersed. So the rest, 11%, this part over here is 11% of the iceberg, and the rest of it, 89% of the iceberg, is fully immersed. And now this example 14.4 was just the tip of the iceberg. Let's look at example 14.5. Sorry, that was 14.6. I was too excited to make that joke. Let's look at our next example, which is 14.5, which is another interesting one, and has to do with Archimedes, this ancient Greek mathematician. So 14, this is example 14.5 on page 426. Archimedes supposedly was asked to determine whether a crown made for the king consisted of pure gold. So the king ordered a crown, and the king wanted to know whether the crown was made out of pure gold as the king had ordered it to be on Amazon. Oh dear. So the king assigned Archimedes this task to figure out whether the crown consisted of pure gold. According to legend, Archimedes solved this problem by weighing the crown first in air and then in water. Okay, so Archimedes was able to weigh the crown first in air, then in water. We are asked to suppose that the scale read 7.84 newtons. Now, Newton wasn't around back then, but we're just going to pretend we're going to use our knowledge of today. So when In air, so you just weigh the crown in air. The weight of the crown was 7.84 newtons. And then if you put the crown in water and you weigh it, then of course, because of the buoyant force, the water is pushing the crown up. So the amount by which the crown pushes down on your scale is going to be less. Remember that scales measure the normal force, and that normal force is going to be less if there's an additional force pulling you up. Think about getting on your scale. If there's someone pulling you up as you are on your scale, then that scale is going to show a smaller number than what it should. So here's the water. The weight of the crown in water, we are told, was 6.84 newtons. So the scale showed 6.84 newtons when this crown was measured in water, and 7.84 newtons when it was measured in air. And we are asked, what should Archimedes have told the king? So with this information, does that tell you whether the crown is made out of gold or not? And so what we should really be doing is we should try to find the density, given this information, the density of this crown, and then try to compare that to the density of gold. So let's keep in mind that what this is showing us, this difference here, is fully 100% due to the additional buoyant force. So this over here tells us that the buoyant force in this case was equal to 1 Newton. So the difference between what the scale read in air and what it read in water was 1 Newton. And we know that this buoyant force should equal the density of water times G times the volume of the object immersed. And we're going to assume that this object was we were told what it weighed when it was in the water. So that is going to mean fully immersed in the water. But we, of course, know how to relate. So this is going to be the volume of the object. But we know how to relate the volume of the object to its density. We know that the density of the object is equal to the mass of the object divided by the volume of the object. And therefore, the volume of the object here, I can replace the volume of the object, so I'll get rid of that. The volume of the object is just the mass of the object divided by the divided by the density of the object. And I should also carry with me the density of the water and G, and that should equal 1 Newton still. But of course, we know what mass of the object times G is. Mass of the object times G is just the weight of the object, which was measured in air to be 7.84. So this is just the regular weight of the object. And so our only unknown in this equation, we know that the density of water is 1,000 kilograms per cubic meter. We know the weight of our object. We know the buoyant force. The only thing we are left to find is that the density of the object, we can solve for that. The density of our object is going to be equal to m times g, which is 7.84 newtons, times the density of water, which is 1,000 kilograms per cubic meter, and then I just have to divide by that 1 Newton right there. And what you find from all of this is that the density of your object was equal to 7.84 times 10 to the 3 kilograms per cubic meter. So that's not great, but the density is 7.84 times 10 to the 3. And we should compare that to the density of gold, which is 19.3 times 10 to the 3, it looks like, which shows you that this is not quite right. So this density here is not the same as the density of gold, which would lead you and Archimedes to tell the king that this is not quite right. So the next part of the question asks, how much would the force read by the scale, how much would the force read by the scale be if the crown was made of pure gold? And to do that, you would just have to substitute this density, this volume of the object over here, which we substituted replace that with the weight that we did just here, divided by the density of gold. So with that, I'm going to ask you to please reach out if you have any questions over email or via Zoom. Please reach out if you have any questions about your final exam. I look forward to seeing all the assignments that you turn in for that. It's been a pleasure getting to know you all, and I look forward to seeing you all in person in the fall. Take care, stay safe, and I'll talk to you soon. Goodbye.